So thank you everybody for showing up today. My name is Jeff Ostermuller. I'm one of the technical solution architects with Cisco. I'm located out of the Philadelphia, Pennsylvania area in the United States, so eastern part of the U.S. I've been working at Cisco since '98, and I've been a data center architect for, I think, the last 8 years. My whole career at Cisco, though, has been focused really around the application space. Really got into content networking back in the late 90s, early 2000s with Cisco, and then it's just kind of stayed working with the applications in the data center for that whole time. When we started putting together this presentation, we focused on 3 or 4 different use cases, or 3 basic customer designs that were pretty active at that point. And as like a trial, I went to a group of SEs. We had 10 SEs come to a room, and I gave them a very extensive diagram of this is what the customer has, these are their business requirements, and this is what they want to do. Myself and one of the other TSAs, we thought we would get maybe 2 to 3 different options. We had 5 or 6 different designs because everybody wanted to use a different box, a different, shiny light or whatever it was. So we decided to focus this down more on not the boxes, but the architecture of what we need to do to be successful. Hopefully that makes sense as we're going through the presentation today. What I found from doing Cisco Live over the last several years was questions come up, and they don't always come up the day of the session or during the session or the next day. If you have a question or something that comes to mind, after this session at some point, please feel free to shoot me an email. It's just my Twitter ID at cisco.com, and that'll actually show up. I can't believe I forgot to put my email address on here. If you could do me a favor, though, if you shoot me an email, just write somewhere in there, like Milan or Cisco Live in the subject, so I actually, who is this random person and why are they sending me a note? So it helps me from that aspect. Also, after today, or after the session today, there's going to be table topics that myself and another TSA that I'm friends with is actually doing by the World of Solutions. So if you have a lot of questions or very in-depth, detailed questions, please feel free to come there as well. And we'll go into more questions or longer answers if you'd like. Make sense? And then meet the engineer tomorrow. I think I have time as well available still. From an agenda perspective today, what are we going through? First, we're going to start with data center evolution, where we're at, how do we get here. We're going to talk about some fundamentals. We'll call it a petite data center or colo facility. How do I scale that, and how do I get to be more scalable? And then something that's getting a lot of attention now is everybody wants to talk about overlays. Oh, I'm going to use an overlay for X, Y, Z. Perfect. Let's talk about them. So I just have some stuff in there. I'm actually doing a pretty large multi-tenancy design right now with overlays. But you have to be careful. There's a lot of things to consider. So as we'll go through there, we'll just talk about some of the considerations and make sure there's a level set. Is that okay? I think we'll all agree that the data center and what we're trying to do in the data center is not like traditional networking. I'm not going to build a campus network the same way I'll build a data center network. I have to take into considerations uptime. How many of us get actually ability to upgrade our data centers at any point in the time? You're amazing, because barely anybody ever does. I asked somebody, I'm like, you need to do a code upgrade. Yes. I have a customer, they called me last week. Their upgrade window for their data center, they just got approved. Guess when it is? August 2015. 8 months away. They just got approval for it. I'm like, you know what's going to happen? In the next 8 months, somebody's going to say, no. There's something happening that month. You can't do it anymore. Right? So our windows to be able to do this stuff is a lot smaller than ever before because it's so critical. The next thing is we have to worry about services, load balancers, firewalls, IDSs, IPSs, security requirements, certifications, PCI. All these things run into the data center, and we have to think about it. The other thing is when we look at these designs, I love this year because what happened? The designs were so simple. It was like a farm of Catalyst 6500s everywhere, right? The data was always coming from the clients to the data center. So 80% of the traffic was in and out of the data center. 20% was in between different tiers. So what did we do? We put 2 6500s in the access tier. We created all our L2 VLANs there, and we had 384 1 gig ports. It was awesome. And then vMotion came out, and mobility, and all these other things with virtualization. And also the data structure started to change. And then our servers, instead of having 2 NICs or 1 NIC, all of a sudden had 16 NICs in it. So now that switch that could support 384 1 gig ports was only supporting 50 servers. And we had problems, but we did this design for one reason. It was incredibly, incredibly resilient, right? Where was our availability zones? Where was our spanning tree problems? It was tied specifically to that one pod. It didn't cascade through the rest of my infrastructure. I love this time. But the world's changed. If we look at it now, 60 to 70% of the traffic stays inside the data center. 20 to 30 or 30 to 40% is north-south. So why are we still doing designs that are these really hierarchical designs to meet the requirements when most of the traffic is actually horizontal between my tiers and not entering and leaving the data center? When I do that, though, a lot of the first designs went back to L2 sprawl. VLANs anywhere inside the data center. And if you didn't do a good job of protecting yourself, you had the same problem that we had 15 years ago. And that problem was spanning tree loops, availability zones. Everything was the same. Everybody was just sprawled across the infrastructure. We have to figure out a way to change that. So some of the things that we're doing now is even though I'll have L2 VLANs extend across an infrastructure, I'll still have a routed domain. But I might route my traffic based on a MAC address. I don't have to route on IP like we did in 2000. Now I can route based on an IP address, a MAC address, or a VNI, a VXLAN network identifier. These are the things I can make my routing decisions on now that I never was able to before. And I'm actually able to, by having that routed domain, I can scale horizontally based on my bandwidth requirements. There's no more. You can only have 2 switches in the distribution tier. You want 2? You want 3? You want 16? Sure. You have that potential now where we never did before. So the designs are changing. The other thing that I'm going through, it's really about human error. Has anybody cut and paste the configuration from switch 1 to switch 2? And you realize that switch 1 was wrong because somebody changed it since the last time you were in it? I'm sure that's never happened to you. It's cut and paste problem propagation, right? It just kind of keeps going. If I look at what VMware did, they created templates and they cloned the templates. Well, why can't we do that same thing with the network? Why can't we create a policy? Or why can't I create a command set like a VLAN structure? I want to create the same VLAN and I want to propagate that across all the switches uniformly. That should be easy, right? It is, as long as I don't use CLI. I got to have a tool to help me to go along with that. So we'll talk about what that is as we go forward. Back in December of this year, I had meetings with 2 customers. One is a Fortune 100 customer, and the other is, well, they're probably Fortune 500, I guess-ish. Both companies use single NICs. They have mandates that they do not dual connect their servers. There's no link aggregation. There's no multiple interfaces out of the server. I was shocked. And I really like the concept that Netflix came out with several years ago. Have you guys heard about the Chaos Monkey? Basically, they go in and break their infrastructure on purpose. They go in and actually shut down servers, shut down NICs, shut down switches, shut down regions inside of an availability zone, just to prove that if there ever is a problem, they can still work and sell movies. That's kind of an awesome paradigm. Wouldn't it be great to go to a server guy and say, I should be able to shut down your server today and not care? What would they do if you did that? Pull the plug on a server? They'd like walk you out the door, right? But we have to get into a new paradigm. We have to get into this ability of, hey, we need redundancy. I should have every single one of my servers dual connected no matter what. Every one of my switches should be dual connected to everything else that I have inside the environment. The network needs to be flexible. It has to be able to accept change. It has to be able to accept what's going to happen or what anybody's going to deploy in the infrastructure. I've had too many times over the last couple of years where I'll have a advanced services person or someone come into a customer and they'll say, well, what applications are you running on the network? And the networking team says, listen, we're building a cloud, I don't know, and I don't care. The network just has to be able to support it. And if I went back 10 years, no, what's this application doing? Everybody wanted to know. And I shouldn't care anymore. I should have the network be flexible enough to be able to adopt to whatever the requirements are. Hopefully you guys agree with that. The next thing that I think is interesting is there's different constructs. There's L3 reachability and L2 reachability. If I'm building something inside of a cloud environment, most people just need L3 reachability, where they just have to have, I just need to know your IP address to send you traffic. That's it. But most of the traditional applications that I'm still working with have a lot of L2 requirements. They'll have L2 keep lives or cluster messages or Microsoft load balancing. Graham, don't get mad at me for saying that. Or they'll have things like vMotion requirements, right? Where I need to have that L2 adjacency between the servers. So I need to make sure that I have that flexibility. The next thing is, whenever I deploy a service, because that's the thing, I build a data center, the data center has services. And I can't constantly create these logical stovepipes to force traffic in certain directions over the data center anymore. So we have to be able to say, when a client comes in and the client wants to get to a web server, what do they normally do? They hit the firewall, then the load balancer, then a proxy, right? Then maybe another load balancer or firewall, and then to get to the web server. I should dynamically be able to support that traffic load for that client. So when I'm deploying things like load balancers, now this slide looks great, right? I have my proxy servers next to each other, my web servers are next to each other. So to actually deploy a load balancer should be easy, right? Because everything's right next to each other. Well, now it's even harder because of the virtualization. And our load balancers aren't always physical anymore. They're sometimes virtual. So you'll see a lot of people talk about NFV, network function virtualization. So now, how do I actually look at that load balancer to say I'm dynamically going to insert it, and I still have to worry about performance, physical or virtual, routed or bridged, or one arm, or source NAT, or policy-based routing, how am I actually going to be integrating into these systems? And then the same thing actually happens with firewalls. Personally, I like to deploy transparent firewalls because I think it gives me a lot of flexibility to say what traffic needs to come to me and what traffic do I not care about, and I'll let it bypass the firewalls. So I'll just trunk certain VLANs to my firewalls that are relevant. But usually, people don't just deploy a load balancer, it's a firewall and a load balancer. These things get chained together. So I have to be flexible from a design perspective to be able to support this. Now, because everything in this world is virtual, and most of the traditional applications that I work with have L2 requirements, a lot of customers are saying, I need L2, right, across a data center. And I'm even getting more and more people say, I need L2 between data centers. Now, I understand that requirement, but I also like the concept that Amazon's gone through, where you'll have a data center, right? So I might look at this as, what is my global data center requirements? And inside of that, I'm going to have a region, and then I'm going to have an availability zone inside of that region, where something can happen to an availability zone that doesn't take out that whole data center. How do I compartmentalize and help provide isolation inside of a physical infrastructure? Well, if I'm extending VLANs everywhere, I got to understand, well, what is the impact of doing that? Also, there's certain things that are constrained resources. So I was really bored, and I didn't want to just hang out with my family in my in-laws' house between Christmas and New Year's this year. So I was watching a whole bunch of different webinars and looking at a whole bunch of different competitors' websites and just saying, well, what is everybody doing? What are people talking about? And it was funny because some of the guys are talking about ARP, and I was trying to think of those ARP scale problems and how do they scale with external controllers and things on those lines. And I started to look at, well, how many ARPs can they handle? 300 to 400 ARPs per second. And I started to think, I'm like, well, Nexus supports like 1,500 or 5,000 ARPs per second. That's a big difference. Like, how do these controllers scale? So I started thinking about a lot of stuff. And we'll go into more of this because when I started to look at the problem, I realized that some of my customers are actually hitting these values on a daily basis. So how do you protect yourself from design? So bear with me for a little while longer. The next thing is oversubscription. And over the last year, 2 years, 3 years, I've seen some really crazy oversubscription numbers. And I can tell you when customers are going to have problems, it's usually when they have buffer issues, things like that, performance problems. one of the biggest cases is oversubscription. So I always look at how many servers do I have plugged into the switch and how many uplinks do I have from that switch up to the next tier. And I try to keep that number as low as possible. 2 to 3 years ago, we said 12 to 1 to 4 to 1 was common. I'm starting to do a lot more designs with 3 to 1 to 2 to 1 oversubscription inside the environment. You have to factor this in just because of servers have gotten so fast. And servers have the ability to push line rate 10 gig without a problem. You'll see it in bursts though. And the crazy thing is, when you look at the interface performance, it might be 2 gigs, but I'm having drops. Why would I have drops if it's only at 2 gigs load? It's because of these bursts that get averaged out over time. So I can do the same thing here when I look at effects design. In this case, it's 24 to 1 oversubscription. I have 32 servers. I have 8 10 giggies out. And then when I get to, say, a Nexus 5K or a 9K, I have 48 10 giggies, and I might have 8 10 giggies coming northbound between these two switches. 48 divided by 6, 6 to 1, or 48 divided by 8 is 6 to 1. 32 divided by 8 is 4 to 1. I multiply those together, and that becomes my oversubscription for the system, server to spine at 24 to 1. If I had a CE7000 from HP, a blade enclosure, and a virtual connect card, they have 8 10 giggies. A lot of people do 1 or 2 ports. More than enough. But when you work out the math, the oversubscription values actually get pretty high. I had one customer who was 256 to 1 because they plugged the C7000 into effects. And that effects had an 8 to 1 oversubscription value to its parent switch. And that had an oversubscription value from the parent switch up to the spine. They had performance issues. Who would have thought, right? So one of these, as we go through the designs, you have to think about it. And you might just say, my servers aren't pushing that much. It's all about bursts. And we'll go through a little bit more of that in a second. Since I had an HP switch in there, I figured I had to put a UCS one in. With UCS, inside of the chassis, it's easy to dial in a 1-to-1 oversubscription, 8 10 gigs, or 8 servers, 8 10 giggies out, 1-to-1. In this case, I actually used 15 chassis, so I had 120 servers, and I used 32 10 giggies out, so approximately 4-to-1 oversubscription. So I usually dial in my oversubscription at the fabric interconnect here. When I look at a Clos architecture, I have my spines and my leafs. I just look at what is my horizontal bandwidth needs and what are my number of ports coming into the system. In this case, I had 2 40 gig ports to each one of my spine switches, and I had 48 ports going into each of these switches, so I was at a 1.5 to 1 oversubscription. Not too bad, right? Okay. But 10 gig in, the first couple examples were 10 gig ports coming in and 10 gig ports coming out. I should probably email you guys all. There's an article from a gentleman that went to Stanford that looked at probability statistics. Honestly, I looked at it, I read the paper a couple times, I'm lost. But I figured he's smart enough, he posted it to Stanford, he got the right answer. He looked at it and said, you know what? Bear with me. I know I can't have 20 ports in a 10 gig ether channel, but let's just assume I can to make my math simple. Deal? He said, if I have 20 servers connected to this switch and 11 are sending out line rate traffic, when you hash that out of the switch, if it's 10 gig in and 10 gig out, as soon as you're over 50% of the bandwidth, you have a 3% chance that 100% of the bandwidth will be transmitted successfully out of that switch. Because of hashing, you'll get contention on certain ports, and they'll drop packets. So 3% of the time, you'll get all your data out that came into the switch. If you switch to 40 gig, 75% chance. 200 gig ports, guess what? 99%. But where's the cost percentage? Well, the cost optics are almost the same for 40 gig and 10 gig, where they've gotten within $100 US of each other. So I'm starting to see more customers just shift over to the BIDI optics because they're only using 2 fibers and they have a better cost structure. So something to think about as you're doing your designs. If you're a lot of 10 gigs in and you're going to something, look at 40 gigs out just from the simple fact of success of throughput. Okay? If costs are the same, bandwidth is the same, you're still going to get better performance on 40 gig. That's just hashing issues. So here's reference, just so you see what version of code supported the BIDIs, and we're good. Any questions so far? Nope, I'll make up my own. All right. A couple base features. So I like this slide because Arcady tells me I'm an idiot because he's like, you know what, Jeff, at 10 gig, we actually, as a negotiation, are on a port, so the port shouldn't come up unless there's bidirectional communication. Or if I use LACP on a port, there's an extra layer of negotiation, an upper layer protocol to prove that the port's active. And my view is I still use UDLD because it doesn't hurt anything. I don't do aggressive mode anymore, but I still enable UDLD because it just verifies that I have bidirectional traffic between the systems. The other problem that I've seen in a lot of designs lately is people are forgetting to set spanning tree path cost method long. Hopefully all of you guys have already turned this on. But if you have a 40 gig port or two 10 gig E ports, they have the same spanning tree cost. So spanning tree has no idea that you have these higher bandwidth interfaces. It should be default, but we don't like to change defaults ever. So guess what? You have to change the default. The other problem, I had a customer, they kept failing ISSU upgrades on the Nexus 7Ks because the switch would stop and say, no, I saw a TCN come through, I'm not going to do the upgrade. That's 10 minutes after it starts, right? It tells you that it's not going to do it anymore. Why? Because the operation team did spanning tree port type edge, and they forgot the trunk keyword for every ESX server. So the same time you get a zero downtime or a minimum downtime to do that ISSU software upgrade is probably the same time the server guys are patching and reloading servers. So every time their server was reloaded, guess what I got? A TCN. It's not that uncommon, so just keep that in mind. Make sure that that's part of the default configurations. LACP, please use active at all possible. I can show you how to create the best spanning tree loop you'll ever see in your life by using spanning tree path or spanning tree mode on one side and configuring an access port to the other. Spanning tree will never recover. It's awesome. So I like to do negotiation whenever possible, and please do not use fast rate. Otherwise, you'll never do ISSU to the system. Cool? MTU has been brought up a lot. I just want to have a quick slide. Set MTU, it's by default on the Nexus 7K on all L2 interfaces. L3 interfaces, you still have to set your MTU. It's not default. If you do FCOE, realize that the QoS policy map for FCOE does what? Resets the MTU, and that overwrites what was done as the default setting. Okay? So I've been burned by that before, so just keep that in mind. On the 5K, you have to set MTU via the policy map, and it will annoy you, and I apologize for that, because when you do show interface, guess what you'll see? 1500, but you've defined it in the policy map to be 9216. So realize you have to look at the class map for that on the 5500, not the interface. In the 5500 and 6K, you can reset it on an interface by interface basis on the last two. I think we covered this already. BPDU guard, it's not on by default. So 3 slides ago, you'll see where I just enabled it globally for all my port fast type edge ports. Root guards, I'm scared of root guard, but if you don't do spanning tree path cost long, don't do root guard. The bandwidths will, you'll have, depending on a failover case, you could actually isolate your switch infrastructure. I'm assuming everybody has done VPCs here or knows what a virtual port channel is. So I'm not going to go into, hey, we have this new feature we came out with 6 years ago called virtual port channels. I'm just assuming you've seen it before at some point in your life. So I'm trying to make 2 switches act like one here. Awesome. You want to dual home things as much as possible, and always use different domain IDs on every one of your pairs in the system. The key here is this slide. There's a great link that goes through all the different best practices that you need to know. There's also a macro that we created for the Nexus 7000 and 626-ish, like that ish, not exactly. I know 626 had it. How about that? That actually goes through, and you could actually just do mode auto, and it'll actually dynamically configure all these things for you and put it into the config, so you don't even have to remember. None of the other Nexus products do that, though. So here's your list. The big one here is auto recovery. So if the peer link goes down, and when the switches come back up, if it can't find its peer, he'll try to stay down. So auto recovery says, if you can't find your peer after so many minutes, come back up, because he's probably shut off too. Make sense? ARP synchronization, if you look at the ARP tables, there's seats up here if you want to sit in the front row. If not, I understand. ARP synchronization doesn't mean the ARP tables are identical between the two switches. It just means when the peer link fails, we do a bulk transfer to update the ARP table on the other switch. Okay? But I've looked for years, I'm like, why aren't they the same? It's a stupid name. Peer switch, make the two switches have the same span tree priority. From a failover perspective, you will not go through a new elect process because you have a new root cost to get to your root bridge. So that one's key as well. And peer gateway, we'll talk about that in a couple upcoming slides, but that's going to be required as well. Here's a peer gateway. Notice when you had like a Nexus 7K, you would always create that L3 link in between the two switches, or Nexus 9K, you create an L3 link in between the two. So I'll have my VPC link, and then I'll have my L3 link in between the two in case there's ever a failover case, I can route in between the two switches. In the 5600 and the Nexus 6000, we can't have that L3 link. It has to be an SVI. It has to be a VLAN. Okay? If you want to ask why, tomorrow night, beer, we'll go through all the reasons. But let's just for now assume I have to have that as an SVI. If I need that as an SVI, Peer Gateway says, here's a problem. NetApp is awesome, awesome solution. But when a NetApp, I build an Ether channel to a NetApp. Think about HSRP. You send an ARP, I give you the virtual MAC address, right? However, when I send you data, which MAC address do I use? Physical. That's like, I use the physical MAC. Guess what they do? And it's not just NetApp. I'm not picking on them. They'll use that MAC address that I sent for the last packet to send it back to me, which breaks VPC because you could actually line up on switch 2 instead of switch 1. So we use Peer Gateway to say, I'm going to intercept my MAC address and my friend's MAC address and the virtual MAC address. So each switch will pick up all 3 MAC addresses. How do I build up a neighbor or a routing table entry when I'm going to pick up your MAC address? You can't. I would never send the packet out because the destination MAC address is something I want to look at. Peer Gateway says, I pick up my friend's MAC address as if it's mine. The exclude says, I do it for every VLAN but this one, or these two. In this case, that's that SVI link in between the two switches. Make sense? So remember on slides, I think it's 17. Honestly, I checked. On slide 17, I said we have some constrained resources. So when I was reading all about some of the other overlays out there, I said, okay, 300 ARPs per second, we can do 1500. I started thinking about, I've been at Cisco a lot of years. When's the last time I had an ARP problem at a customer? And I'm like, maybe 10 times over 16, 17 years I've had this as a problem. Not that common. So I started looking, I said, well, what are the issues? Well, it's 128,000 ARP entries, and I can learn about 1,500 or 5,000 depending on the supervisor per second. A couple more than a few, right? Well, I went to 2 of my accounts. One that's still running 525, one that's running 6210. I'm like, hey, bud, issue this command. And they looked at, in that control plane policing policy, how many drops they've had. Look at that bottom one. 128 million packets. Not bytes, packets. I did the math to figure it out. They're losing approximately 1 million ARPs per day. They're throwing away because it's exceeding 1,500 ARPs per second. You know how many 1,500 ARPs per second is? That's a lot, right? So when you think about availability zones and control and scale, I got things I got to think about. So this caused me like a couple sleepless nights because I'm like, holy cow. One, none of my, so I sent to 4 accounts. These 2 had the most drastic failures. So I included those 2. I was shocked. And they had no idea this was happening in their environment. So I'm like, okay. Now, out of those 10 issues I've had, one was because somebody improperly disconnected a data store and the server, the virtualized host, blew up and started sending in 10,000 ARPs per second. That was one failure, but that box was rebooted at some point, so I've lost those counters. But they're seeing about 10,000 ARPs per second based on a data store being improperly removed. So I said, okay, well, this is an ARP flood. What is an ARP flood 2? So if I looked at 2,000 ARPs per second, if I'm the switch, I'm throwing away what? Anything over my max performance. Control plane policing will stop you at about 1,300 ARPs, okay? So anything over 1,300 ARPs per second, we just throw away. What's better? A server ARP? A router ARP? A switch ARP? A storage SAN ARP? How do I determine it? I don't know. By default, an ARP's an ARP. I can throw away your ARP or your ARP and not even care. So how do you know? Well, when you have these floods, what's your ARP timeout on a Nexus box? It's on the slide, guys. It's 25 minutes. So after 25 minutes, if that problem is still going on, my CPU will be about 70% if it's a SOUP 1. SOUP 2 is a lot less. SOUP 1 is about 70% CPU. But it'll be, after 25 minutes, you can start actually losing your routing adjacencies. Crazy, right? Like, that's a big deal. So here's the math to figure out the control plane policing and what I throw away and how to adjust it. But the biggest thing is, how do I make sure that I know if something happens? A tree falls in the woods. Do I care? Well, if it's right next to my house, I care. But if I'm not home, this one will act, if by issuing this log command, it'll actually tell you when control plane policing throws away a packet or throws away a lot of packets. In this case, I said after 100 packets that you throw away during that interval, send me a message. So that's the output. Perfect. Now, if you care about, well, what is a good ARP? My routing adjacencies are good ARPs. You can actually create a new COPP policy. I can take, don't shut off COPP. Please do not shut off control plane policing. That's probably the worst thing we can do as a group. Leave control policing on and modify it. So I'm going to create a custom policy, and then inside my custom policy, all I'm going to do is look at my critical devices, and I'm going to exclude them from the generic policy. And what happens then? Dude, I can put a new value for those. One thing to think about here, though, is control plane policing works from top to bottom. So I have to insert before, if I created a new class for my special ARPs, I have to put that before the generic ARP one. Otherwise, this policy will never be hit. Does it make sense? Cool. The other thing is I can tune it. So my slides, I guess, are out of order. The top section is how to create the custom policy. Okay? The bottom section is in 6.2.10, I think. It's out now. 6.2.8, 6.2.10. We created a span on drop, which means that if I'm spanning traffic, I can say, I want to span everything I'm going to drop. That's cool. Like, that's really cool. So I created a span session, source exceptional all. So now any of my L3 transmit drops, guess where they go? My sniffer port. So now if you don't know why you're dropping packets, guess what? Send them to a sniffer. It'll tell you. I like that. And then if you're dropping a lot of packets, your CPU will spike because of that. So if you really want to track it, this will actually go through an EEM script, where we'll look at an SNMP MIB and actually write an output file when you're actually dropping the packets. This is a reference. I'm not going to go through every line if you don't mind. In the SOUP 2, though, you have to know the extension ID, in this case 26 or 27, and that gets put at the end of the MIB, so you're pulling the right module. Also, did you guys know that you can download vNXOS, a virtualized version of NXOS? It's really cool. So I'm running vNXOS on my Mac. Like, it doesn't do Outlook or anything like that for me, but I can actually do L3 simulations for what I want the configs to look like. There's no L2 forwarding, but there's L3 forwarding. What I like about it is it's actually running 7.2 code, so it has an API that I can externally connect to. Inside of here, I just did config T VLAN 123. This is also in the Nexus 9K today, and I believe it's the next release on the Nexus 7K, Nexus 5500, 5600, 6000 that'll have it. I think it's Janjuk for the smaller fixed platform switches, and it's Gibraltar for the 7K, but it'll give me this API there too. So now I issue these commands, it'll actually, through this API, it'll actually tell me what would be like an RPC call that is sent to the switch. And then when I press post, it'll actually even tell me what the answer is coming back from the switch. Kind of cool. But here's that cool button. I am not a Python programmer. I was in college a lot of years ago, and that's the last time I did software programming. I know I look young, not as young as I look. So I press Python, and guess what it does? It gives me the config. It shows me a Python program. I'm like, it made it itself. Haha. Now, it's a little wordy. I'm kind of annoyed by it. So all I did is I basically consolidated those long lines into smaller lines just so it's easier for me to read. Okay. It should have done that, I guess, from the tool, but it tries to make it look pretty. There's seats up here. Now, whatever you want. Since I'm not a Python guy, there's a guy named Kirk Byers out in California, and he was running this free class on Python programming for network engineers. And every Thursday, he would send me an email to watch a YouTube video, and every Tuesday, he would give me like a homework assignment. I never turned in the homework, and he never complained. So it's not like real school. But he doesn't want to teach you all of Python. He wants to teach you enough so you can do basic programming from a networking side. Kind of cool, right? So I took his class, and I'm like, hey, this is simple. All I did is I created a list. Guess what that list is? All the switches. I only put 2. Could I put 100? Yeah. But I only need 2 for an example, right? And then I have my username and password. You can actually put this in as an input so you don't save the password in the script. And then it's also tied to the person that's making the changes. Kind of cool, right? Then all I do is I say raw VLAN, raw input, and I actually put up inner VLAN to be configured. So now, think about it. How often are you creating a VLAN in your environment? Does the operation team do it, or the architects do it, or the engineering team does it? Well, why don't I create a template, a runbook that says, just so nobody messes up and it's identical on every single device, I'm going to create this one script, right? So now they issue a Python command. Python, add VLAN.py, enter. What VLAN would you like? What's your username? What's your password? What group of switches would you like to configure it on? So now I can go out and push this all the config down. Pretty slick, right? Now all I did is a for loop that was not in the example that the GUI gave me. And how do I learn how to do a for loop? Well, I stole code that, Kirk used in an example. I'm like, this is easy. There's also a ton of examples on GitHub. So www.github.com/datacenter. There's a gentleman here named Paul Lesiak who actually submitted a ton of examples up there for review. They're just, we want you to take them, we want you to change them and make them your own. Also, in this example, I changed it from HTTP to HTTPS. I figured I didn't want unencrypted traffic going to my switches. That'd be like using Telnet in 2015. I know some of you probably still use Telnet, and I do in my lab too, but I'm trying to be more secure. To do this, though, I either have to install a cert on all my switches, or I just say, don't look for the SSL certificate on the switches. I know it's going to fail, right? It's false. Don't validate the cert. Cool? Now, when I talk Python, I've shown this to SEs, I've shown this to customers. Most people say, this is 3 lines of code, Jeff. Config T, the VLAN, exit. You have a 26-line program. You've got to be kidding me. Yeah, but I write that once, right? And now it's reusable 1,000 times, and it gets synchronization across all my devices. The next thing is, there's a lady at Cisco called Shahab? No, let's say Shavi for now. She'll complain if she ever listens to the recording. I can do something simple that says, check all my VLANs, right? Create a list that says, here are all the VLANs I need on the switch. It can go out and actually check every switch, compare it to a list of VLANs I have on the switch, and then dynamically reconfigure all of them. One of Paul's programs on GitHub is something really cool. It does shows CDP on every switch and looks at your neighbors and the destination port and makes that a description on the interface. Because whoever goes back and fixes the description on the other interfaces, like, I know there's always somebody that does, but I never do. So I need Paul's program, right? And I just say, show CDP, fix it. Write the descriptions in all my boxes for me so I don't have to. That's cool. Do you want to change it to LLDP? Sure, go to the script and modify it. It's free. All right. So here's my petite data center because small was deemed inappropriate. So what do we have? Are you guys still with me? There are seats if you guys want to sit down. If you don't, I'm fine. I got to stand. So what do we have? All right. And this is because when I worked with the SEs and we started going through the examples, I had too many people that had too many different ideas, so we just removed the boxes, but I want to talk about the design architecture instead. So we had a customer that came back, and they were building out a colo facility. They were already a Nexus fabric. They were using VPCs across their infrastructure already. It was just what they standardized on when they first started deploying Nexus about 5 years ago. So as a VPC type customer, we said, all right, well, what do you want for a small colo? They said, I got 50 servers that have 2 10 gig ports. I have 100 servers that have 6 1 gig ports. Okay. IP-based storage, VM ratio is about 30:1 to 50:1. That's their oversubscription on the servers they're buying. Okay, not a problem. All the servers are dual attached, and we started figuring out, well, what's the math? Well, if I have 150 servers, I looked at the worst case of 50 MAC addresses per server, right? 50:1 consolidation ratio. I'm like, okay, I'm at about 7,500 MACs that I have to worry about. The reason why this is so important is when I look at some of the switches, they might only have 32,000 MAC addresses, and they might only have about 30,000 or 28,000 that are actually can be active concurrently. We potential maximums, and then you look at CAM table and what actually fits in real life, you'll see a little bit less. Okay, collisions. I said, all right, great. 7,500 though, it's way smaller than anything we support. So I'm like, we have options. One of the options is actually to use just 2 switches, like 5600, 9Ks, whatever, and then just create a bunch of fexes below it. And if I look at it, I would need a total of 18 fexes to kind of meet the design requirements. It's approximate, because you can do 2348s now, you can do 2248s. So I could actually have 18 fexes, and I could dual home them to 2 switches. And we look at the switches, the next 7K, 5600, how many fexes do they support? More than 18. So you could conceivably, I'm not saying to do this, conceivably though, you could just have 2 switches with a whole bunch of fexes hanging off in between them. And then the argument or the discussion would be, how do I connect my servers to the FEXs, and how do I connect the FEXs into those parent switches? If it's a 7K, the FEXs have to be singly attached to each 7K. So this FEX can tie to 7K1, this group of FEXs will tie to 7K2. And then the number of uplinks that I have is determined based on my oversubscription values that I'm going to work with. Okay? And then my servers are going to be dual attached, hopefully, to both of the FEXs that are down below. And you can get pretty good scale. But we still want to think about, though, what do I have? Well, I have some scaling concerns personally. Just because I support that number of FEXs, it depends what are going on. Because you think about it, everything that occurs on that FEX has to go to the parent switch, and that parent switch is responsible for it. If there's 18 FEXs on one switch, that's a lot of ports. You're talking about thousands of ports hanging off of that one device. So keep that in mind when you're doing your math. Also, if it's a 7K, it's really not 18 switches per or 9K. It's actually only half that. Because half the FEXs are on one parent switch, the other half of the FEXs are on the other parent switch. Right? What I like to think about, though, is my ARP learning, my MAC addresses, CPU level, port up, port down, what's going to be punted to the CPU. My spanning tree scale shouldn't be a problem here. Port channel numbers is small enough. Oversubscription. Failure domain, though, is kind of important. And I always, whenever I do a design, I just try to strive to make sure that I have ISSU capable. And that's a big deal. I'm actually doing a Meet the Engineer session tomorrow with a gentleman, and it's about ISSU on 5Ks with FEXs. And it's dual attached. He's like, how do I make this work? I'm like, what does it look like? I'm like, ooh, he's going to have a hard time. So as we go through the designs, we just want to make sure that we kind of take in consideration what to be successful. The next thing, so I have a couple more on this in a minute. The next thing is there's certain commands that are being more important. So if people are looking at things like VXLAN, realize that there's a control plane that has to happen. If you do the standards-based VXLAN that's based off of the RFC, the control plane is flood and learn, and it requires multicast as that underlay. And you also have to worry about head-in replication, broadcast unknown unicast and multicast packets. Who's going to replicate those? Does the controller replicate it? Does the host replicate it? Or does the network replicate that traffic? Because all three of those are different. So I know not every customer I've worked with has deployed multicast at all. So we're in slide 54. We'll go back to this in about 100 slides. But here's the multicast configuration. There's a couple things you have to do. First, you enable PIM. You enable routing protocol. Do I care what the routing protocol is? No. You want to use RIP? Go ahead. I'm just using EIGRP because it makes my example simple. I then define a loopback address. And this loopback address is one that's actually tied to the switch. I want you to look at the loopback one, though, on both switches. This is going to be my aggregation switch, or my spine. They're duplicate IP addresses. Isn't that freaky? Nobody cares? Good. I think it's freaky. So I'm actually creating a redundancy by using the same address through Anycast RP on both of these devices. Then I create basically this PIM RP address, my rendezvous point address, and this is pointing back to loopback 1. And then the group list is, well, what multicast can I basically become a rendezvous point for? And check this out. I'm actually telling it, here are your redundant Anycast servers. Here's the virtual IP address, the loopback 1 on both the systems, and then this is the system's real IP address that I'm going to be routing for. So if you're going to try to get to 10.10.10.50, you're really going to send that traffic to 10.1.1.4 or 10.1.1.6. Make sense? That's how we get that extra level of redundancy in the systems, where they're backing each other up. So as I'm doing these designs, 7Ks, even if I'm using the 6K as my aggregation tier, turn on your multicast, get it out of the way. It's a simple config. It's solid. It's been around for forever. Let it go. As I do this, though, I'm going to set that up on my spine switches. On the access tier, there could be fabric interconnects, it could be FEXs, or it could be more switches. I'm seeing more and more customers actually go to more top-of-rack switches and consolidate their servers directly in versus FEXs. It's just, in the last 12 months, I'm seeing more of it. As the switches keep getting cheaper, the FEXs have stayed the same, I think, their whole life. They're faster, they're bigger, their 10 gig ports are now the same price of that switch, is the same price as it was 6 years ago. But the switches, the parent switches have dropped in price, or I'm sorry to see people just buy more top-of-rack switches instead of less FEXs at this point. They're not going away. The 2300 just came out, does local switching. It's like almost a switch at this point. It's kind of funny. When I bring out these two switches, a couple things you want to keep in mind. In the first slide, that was like a 7K. Or in this case, though, if this is a 5600, remember, I'm going to probably route out. Now, this routing could occur at the aggregation tier or back at an access tier or a leaf tier. We'll go through that in a little while. If this is a 5600, though, I need to make sure that I have that L3 interconnect in between them, and that has to be an SVI in between these two switches. Remember that slide a little while back? And then I got to do that peer gateway command. The other thing to keep in mind is, I got to check my next slide. My keep alive port and how I'm actually defining the keep alive. Because in a VPC, I have my peer link, which is always 2 ports at a minimum, unless you have a lot of multicast traffic and a lot of broadcast traffic, because all your multicast traffic does go across your peer link. Most people kind of forget about that when they're doing their planning. So if you're a large financial that does a lot of multicast, you will have more than 2 ports for your peer link. You might have 4, you might have 6. It depends on how much multicast you have inside of your environment. As also, when I'm going through the peer link, oh man, I don't like that button. As I'm going through the peer link, if you actually read, because I never read it either, if you read the documentation on VPC, it'll tell you that on the 7K, the best way to define the peer link port, or the keep alive port, I apologize, the keep alive port, is through a front panel port. The second best method is to actually use the management interface. On the Nexus 5K, 5500, 5600, 6K, a lot of people assume that the best way to define the keep alive link was using front panel ports. But if you define it with a VRF and using front panel ports, guess what makes it harder to do? ISSU is almost impossible. Because you have to create a VLAN for that keep alive. What's one of the things that doesn't allow ISSU to work? That switch, the 5K, cannot be root for any VLANs. Because when we actually do a software upgrade for one of those fixed platforms, there's only a single soup. If there's a single soup, what happens? I got to reset the control plane. What happens when I reset the control plane? We lock the data plane, so the data plane keeps forwarding traffic, but what happens to the control plane? It reloads. We just don't affect the data plane when we reload the control plane. So what's something the control plane is required for? Besides routing protocol updates, because I can fix that, right, with NFS. But what's the thing I can't fix? BPDUs. They come out every 2 seconds, whether you want them or not. So that BPDU hits, I can't not send out a BPDU because then I'll cause a failover, right? People will start timing me out. And if I'm not the root and so I need to forward it, I have to actually change the bridge ID and the priority when I send it downstream. I'll stop doing that in an ISSU update. So I can't be root for any VLANs. So guess what they do to the peer link? You have to shut off spanning tree on that port in between the two, which scares me to death. Because what are the chances that somebody will forget that's only for the VPC keep alive port and shrunk that because they'll just do switch port, switch port shrunk, allow all. Like who doesn't type that command in, right? It's so much easier than defining what VLANs you need. So if somebody makes that mistake, now I have another VLAN going up to my spine that doesn't have what running on it? Spanning tree. That's got to be a bad idea. So when you do this, especially in the DSPU switches or the fixed platform switches, you always want to make sure, or I would strongly suggest, that you use your management port. Can you make it work without that? Yes. It's like network. You guys know MacGyver? Yeah, like it was a great TV show, right? I can fix it with like duct tape and garden hoses and baling wire, and we can force it to work, but that might not be the best idea. So just keep that in mind. I can force it to work. Also, you don't want to connect UCS into effects. I have a customer that has done that. It's not good. Oversubscription, buffer problems, lots of stuff. So you always want to make sure that the fabric interconnects connect directly into a switch with local switching capability. I do have a lot of customers that like commonality of design though. So in a lot of cases, if I'm using the fixed config switches, like the 5600s, in a lot of cases we're starting to see I'll use 5600s in the leaf layer to basically feed out my FEXs, my remote line cards there, and I'll get some reasonable number, 8 to 1, 6 to 1, where I'll have 8 FEXs or 6 FEXs below a parent switch. And that kind of keeps in line my oversubscription values. If I start getting into 12, 20, they work, but keep in mind that's your failover, that's your availability zone. You're allowing all that stuff to cascade up. And then I'll actually bring that upstream into another pair of 5600s, like the new 40 gig aggregators, that sort of thing, and I'll actually do all my L3 at that point. That'll also be where I have my rendezvous. If I'm doing that L3 though in that box can't do ISSU. However, if I've redundantly deployed them, I should be able to take one of the switches out and let the other one still run. Just so you know, in the next major release for the 7K, it's we're going to call it 7.2, Gibraltar internally. We're doing something called maintenance mode. So we're doing changes to basically how fast it takes to upgrade the box, how fast reload times are, things like that. But also maintenance mode allows us to start dummying out ports and changing weights from a routing protocol perspective and a hashing perspective to take the switch logically out before it shuts down the ports, so you can actually, it helps you remove it so you can do a code upgrade without having to worry about ISSU. I think it's kind of cool. It's like it's stuff you can do yourself. It's just we're creating macros to help you basically do it. If you're doing a 5K design though, I do have the ability to do a dual attached FEXs only with the 5600, 5500, and 6K. The Nexus 7K and the Nexus 9K do not support dual attached FEXs at this point. So I can't have effects connected to both switches.
Do you recommend to dual attach the FEXs?
Do I recommend to dual attach the FEXs? I had a lot of cases over the last several years where customers have single NIC servers and dual NIC servers. So we used to create these pools or these cabinets. These FEXs over here for single attached servers, and they're dual connected to 2 parent switches. These are for dual connected servers, and we would single attach those FEXs. And every customer I did that with hated me after about a year because they're like, listen, I got room here, I don't have room over there. I have power here, I don't have power over here. Enough of the madness. I want one architecture for connectivity. So whether I like enhanced VPC or not, and dual attached FEXs and VPC down to the server or not, it doesn't matter. That's why I've had it deployed at a lot of my accounts. So we're trying to actually get that functionality into the other switches, but we kind of held off for years because think about it. We had dual soups. I'm like, we had tons of redundancy built into the chassis. We're like, do we really need that extra level of redundancy? And we're being asked for it now though. So in the smaller switches, I do dual attach the FEXs in most of the cases anymore, and I try still to dual attach the server to 2 FEXs. I do have one customer that dual attaches servers, but a lot of times they dual attach them to the same switch, which I'm like, it didn't help. But mistakes, right? 2 different teams, sometimes language barriers of how people talk about things, whatever. In this design though, you really, what did I do? in this design I actually didn't use FEXs. So this design was all FEX-based architecture. In this case, it was a recent design. It was all done with Nexus 9300s. So we used the 9372s are all the switches down here, and the 9372s feed it into the 9332s, and those are just 32 ports of 40 gig. So it changed the design structure. Because think about it, if this was 3 years ago or even 2 years ago, what box would we have needed to have that much 40 gig? A pretty big 7K. In this case, now instead of using like a 13 RU box or a 12 RU box, I'm down to a 2 RU box, and I'm at 32 40 gig ports. So if I don't need all those features and capability, we're seeing designs shift pretty dramatically from a cost structure and also an RU and power structure inside of the data center. Everybody's out of space, right? So using these smaller high density boxes sometimes work. Question? No? The other thing that I'm worried about is services and where they're getting deployed and how am I going to actually interject traffic. Because no one deploys just a data center. Everybody has stuff like services to go along with it. And when I look at it, I have a couple options for my services. If I deploy them as virtual machines, deploy them as L3 endpoints. That's where we'll be successful. If I have it at a centralized location, which is still a common config for a lot of customers, I'm usually doing that somewhere at like an aggregation tier inside of the infrastructure. I bring in my firewalls and I'll bring in my load balancers up there at that point. When I'm up there, my firewalls, transparent, routed, both work really well. If I'm not, we don't make a load balancer anymore, right? We partner with Citrix. We partner with people. We don't actually create load balancers anymore. And when we used to sell the ACE, we used to have a lot of customers that did transparent mode on their load balancers. I'm not doing that as much anymore. I'm trying to get people out of transparent mode and actually back into routed or one-arm designs. Especially, I've been more successful. How about that as an answer? I've been a lot more successful when I've done that on anything but ACE. So if you're still a transparent fire or a transparent load balancer shop with ACE, think about transitioning because you only have a couple months left to support and software updates. Hardware support's pushed out a little bit. Software updates almost done. 72 days, I think, last time I checked. So you really want to start looking at routed and one arm for those. We do have something called RISE though, which I'll go into. We actually created this for ACE, and we deployed it right now with Citrix and with the NAM module. It allows us to actually deploy, and I actually am doing this on a lot of accounts right now. It allows me to have the load balancer look like it's a module inside of the Nexus 7K. And the next release of code for the Nexus 5500 with L3 modules, 5600 and 6000, guess what they get? RISE. So now, it's a pretty slick design because it allows me to look as if that module is deployed directly into the chassis, even though it's VPC connected and it might be multiple switch hops away. Why is this cool? Well, first, it looks like it's in the module. I can session to it, I can attach to it, and actually configure it directly from the switch if I wanted to. Not saying you're going to, but it looks like it's a module from that aspect. The other thing is, I can dynamically inject rules to forward my traffic back. Because inserting the load balancer is always the hardest part, where I basically use networking origami, right? That MacGyver, duct tape, baling wire, all that stuff, garden hoses, to force traffic like these logical stovepipes. In this case, what do? You change the design. I'm dynamically using policy-based routing, and we're calling it auto PBR. Excuse me. In auto PBR, based on what the services that are running on that server, we dynamically put in a policy-based routing command to force the traffic back to the load balancer in the return direction. The service goes away, guess what we do? We remove that PBR command. So it's based on the health of the servers and the health of the VIP for what gets actually redirected back to the load balancer and what doesn't. So now it's no longer building these Excel spreadsheets with a whole bunch of VRFs and policy-based routing. I'm logically, based on my load balancer config, doing this. The server team creates a new load balancing rule. What do? It's dynamically deployed. We dynamically set that up on the switch. It's kind of cool, right? They don't need the enable password. The server team doesn't need the enable password to the networking device anymore. But based on that configuration, we're dynamically enabling it. So based on health, I do my auto PBR, so now I know what I need to redirect. The client comes in, it sends a request, and it hits the switch. We route that to the load balancer because it's going after the virtual IP. We get it, we send it back to the switch, it routes to the server. We don't change the IP address. So now the security guys don't even get mad, right? The server guys' logs match the server's real IP. Now the server responds. Ugh. If I learned my mouse, I'd be in a lot better shape. The server responds, it hits the 7K today, next release for the other platforms. Auto PBR will pick that traffic up, forward it back to the load balancer. And why is this so critical? The client made a request against the VIP, not the server's real IP. So if I don't intercept it, send it back to the load balancer, he can't change the destination IP address. So I have to renat the destination IP before I send it back to the client. So now it gives us the ability to dynamically insert it and also remove it based on availability. So give you an idea, we're going to talk about that more Friday, 9 o'clock. It's a whole session on it. If you want to come. There might be free t-shirts. I don't know. I seriously think there is. Not for everybody, but for questions. What else do I have? Transparent firewall insertion. So when I talk to a customer that's doing like, I don't know, something crazy, like PCI certification or HIPAA for healthcare or NERC for nuclear reactors in the US, they don't need all VLANs. They need a subset of the VLANs to go through firewalls, to isolate themselves. My personal preference, multicast still works, my routing protocol still works. I put the firewalls in transparent mode, and I trunk just the VLANs that I need over to the firewall. And then I bring that same trunk, I send that back in. Now, I like to do a VPC connected on my firewalls, so I'll have my unsecured, my secure VLANs on the same port channel in a lot of cases. And the auditors have been okay with this so far. But that's what I like to do. I have seen it, though, where depending on your config, I'll see more ARPs in the system in transparent firewall mode, and I'm still trying to figure out why. But this gives me a better scale, too, because it allows me to horizontally scale my firewalls based on my needs by what VLANs I'm trunking to them. Because think about it. These are 40 gig ports, right? There's a lot of, or multiple 10 gig ports. How much can a firewall really do? So you want to scale kind of horizontally based on your requirements of performance. And if you send all traffic there, you could have problems. So I only like to send what's required. Now, I do have several customers that say, no. Your switches are L2 only, and all the L3 is going to be done at the firewall. All right? It's not really great for me, but we can do it. The biggest thing I found by doing this design, though, with the firewalls are the L3 control point. I don't have a lot of availability for route health injection, for understanding what's going on with the load balancer. Auto PBR doesn't work unless I define VRFs and interfaces that are deployed on the switch. So if you're doing L3 in the firewall, just realize there's things that you're not gonna have the flexibility to do. I personally like to do VRFs in this case, but this is an option. If you do all L3 on the firewall itself, you're probably going to have to do this command. If there's any L2 heartbeats, cluster messages, things like that, the Nexus boxes run multicast by default. They run IGMP snooping. There's no RPs. Guess what happens to the traffic? We don't forward it. So go to the VLAN where you have the servers that have the L2 requirements or the heartbeat requirements and actually shut off IGMP snooping for those. You can do couriers, but guess what you need when you define the couriers? An L3 interface. If you're going to put an L3 interface in, you might as well define a VRF and not do L3 in the firewall. Just my opinion. What's that? Oh, the static multicast router ports? You can put a, so the question is, I can put a static, a multicast address on a physical port itself.
No, it's just you tell the switch to forward the traffic to...
I usually just do this, where I just shut it off. You're right, there are multiple ways to solve that problem, though. Yeah. In my perfect world, because I live in this, like, you know, castle with a throne, and you guys are responsible for daily operations, and I just say, huh, you did that? Why? Huh. It's easy from my side. So in a lot of my deployments with firewalls, though, what I like to do is still put L3 on the switches themselves, and I use VRFs, virtual route forwarding tables, so I can create different L3 instances on the switches that are completely isolated. So I have one pair of 7Ks that have 1,000 VRFs on them. It's a couple more than a few, but that's the scale that the customer needed. Now, it gave us the ability to have a whole bunch of clients with just complete isolation from each other on the same physical hardware. In this case, probably fewer, but I still like to do that VRF to isolate my VLANs from each other that I require. I bring them up into different VLANs into the firewall, and I use that to create that isolation in the firewall. And then personally, I like to do BGP through the firewall and create my neighbor adjacencies. That way, I'm basically proving that the firewall's up, and it gives me a very effective way to get my routing through the firewall effectively. You can do routing on the firewalls, but I'm not a security guy, right? I'm a data center guy. What do I fall back to? The stuff I know. And I know this always works. And it gives me a lot better scale than worrying about the routing entries on a firewall. I'm like, firewalls are protections. They're not routers. This is a router. In this case, I'll actually define a lot of VDCs in conjunction with my VRFs, and I'll have one VDC for the outside, another for the inside, and I stitch those two VDCs, the virtual device contacts, together with the firewalls. If I add in the load balancers with this, the firewall design doesn't change. I like to still do those in transparent mode. The load balancers, though, I usually define as L3. I like to do them in one arm mode if I can now. So the next version of code, I get RISE on the smaller switches as well, which will give me better commonality across my different products. And then I'll do dynamic PBR or auto PBR on those aggregation switches feeding up into me. The only time this doesn't work, because I always like to do a VPC connection from the load balancer to both spine switches, the only time this doesn't work is if I want to do routing on the load balancer. So there's a common design for dual data centers that people use called route health injection, where you'll actually inject in this health state of your virtual IPs via a routing protocol, OSPF, BGP, RIP. What's the problem with that? Well, if I'm routing through a VPC, I get into basically adjacency problems because we're using pure gateway. So I could actually make a routing decision that I want to send this packet to switch 1 and another one to switch 2, but because of a VPC, the packet that's supposed to go to switch 2 might go to switch 1. And what's our rule for that? Well, I can't send that across the peer link to the right switch, and if I have pure gateway on, he would try to intercept it anyways. So I wouldn't be able to configure my pure gate where my routing entries just wouldn't work. To get around that, if I'm routing via this, I'll actually do an Ether channel configuration instead of a VPC configuration. I only tie to one switch. So each load balancer will only tie to switch 1. This one will tie only to switch 2, and then RHI would actually work in between the two systems. Make sense? When I scale this up, I have the ability to create these repeatable building blocks just to do that horizontal scale that I need. When I scale it, I like things that are repeatable, so it always just works. So in this case, I can say, great, I'm going to have 6 FEXs attached to each set of top of rack switches. The top rack switches are going to dual connect into a 7700, let's just say for an example. And if I do this from a design perspective, I can have 2 10 gig ports per server, 96 servers per pod, 192 10 gigs per pod. I can scale to thousands of servers very easily in this design. And a very small oversubscription ratio. In this one, when I worked out all the math, I was about 6 to 1 oversubscribed with 40 gig northbound ports. Not bad. So I like that from a design perspective. Its repeatability is what I like about it. We do have a couple issues that we will talk about in a couple slides. Now, when I go through this, though, let's just say I had a different blade enclosure. These blade enclosures can be either VPC attached, or they can be straight through Ether channels. If I use virtual connect cards, C7000s are common, right? The condition with UCS. If I have those, I like to actually, virtual connects, I actually do standard Ether channels with, because I don't have a lot of troubleshooting for VPCs in case there was an LACP problem. I don't have a lot of visibility to the switch, so I like to just go to a simple Ether channel for those. If I do FEXs, I usually dual attach my FEXs, just design. Also, it depends how the switches are configured. You can actually set them up as active-active or active-standby, active-passive. And they behave differently from an earthbound connectivity perspective. So if it's a virtual connect card and active-active for two virtual connect cards in the same chassis, they don't actually share traffic in between the two virtual connect cards, because that would actually create a span tree loop. So what they do instead is these two ports on virtual connect 1 are for like VLAN 10. This one, they actually create internally a new VLAN for the ports going to the second NIC on all the servers. So that way they can do active-active out, but they don't do east-west in between the two. So if I'm doing an active-active, I usually will see a lot more traffic going across the peer links. So just realize that if the server team's using active-active with the C7000, watch the links, because you might need more than two on your peer links if you have a lot of east-west traffic in those chassis. If it's active standby, two ports won't be sending traffic unless these two ports fail. So there's plus minuses to every design that you just have to kind of weigh out. And if it's effects-based, I just VPC them, and the northbound switch is what actually handles all the traffic for me. And since I'll actually favor so let's say, for example, it comes through server 1 is trying to talk to server 16 in the same chassis. If this one came through port 1 through FEX 1, it would hash to this switch. If it had to come back down to the other FEX module, it never leaves the switch. It just hairpins and goes back down to the other guy. So I won't go over the peer link for that if I'm staying inside of the same chassis. And again, we brought this up with UCS earlier. Everything is active-active. Today I can use a total of 32 10 gig northbound ports, and I can have 8 interfaces out of the enclosure itself. So you can get very, very low oversubscription. When I go through these designs, though, especially on the 7Ks right now, the 7700s, different modules have different functionality. The F2 modules, smaller routing tables, smaller buffers, smaller MAC address tables, doesn't do a lot of the features. OTV, MPLS, those aren't enabled on the F2's modules. They are on the F3 module. The F3 module also has 4X. It supports OTV. It supports MPLS. It supports a lot of the extra flexibility. So I have options there. So if I'm carving these up, though, from a design perspective, I do like to use the F-series cards facing down towards my servers. However, if I have a lot of oversubscription, I like to use the M-series cards because of their buffer structure. They have a lot bigger buffers and a lot better capability. So I'll actually use F3s facing down. I'll use the F3s, interconnect them to an M2 VDC, and I'll create that as my core. And then I'll usually, in this case, if I had to do OTV, I'd actually define that OTV on the core VDC itself. Because the rule that we have with OTV is I can't bridge and route at the same time. So I look at it as I can't be the L3 interface for that network and do the L2 extension at the same time. So if I'm doing the SVI in the F3 card, I just have to trunk that VLAN up to the core VDC, and he can do OTV at the same time he's doing routing for the rest of the infrastructure. They work together. I'll do VPCs are actually done between the two cards and the F3s. My core is only routed, and I won't actually put the VPC peer links on there because I'd rather just do VPC or routing at that point. If you wanted to, you can create another VDC just for OTV. But again, if I'm using my aggregation for my F3 cards down, that core can actually do the OTV function for you unless you want to actually create a different VDC based on each role that goes on inside the environment. With VPCs, though, what I've seen over time is complexity, and it's usually around the configuration as these start to scale out. So if I'm doing 3,000 servers, that's one availability zone. That's a lot, right? I might try to break that up just from a risk perspective, because everything that happens with a VPC, it's got to match. So let's take, for example, if we go back in time a whole bunch of years, and let's say I had that 6500 design from 2000. I have two 6Ks, and I have two more 6Ks underneath it for access. Two for aggregation, two for access. Let's say I did L2 between all those 6500s. And let's say, anybody make this? I know you guys, somebody that you work with might have made this mistake at some point. You ever go through and do, hey, I got to add this port, or this VLAN to this new trunk? So I'm going to do, config T, interface 1, 2, 3, 4. I'm going to do switch port trunk, allow VLAN 10. And they forgot that add keyword, right? Because there's already 100 VLANs on that port. But they didn't type add. Why? Because it's 2 o'clock in the morning, because that's the only time you get a change window. So what happens? Well, you only get VLAN 10 on that port now. In the Catalyst days, was it that bad? No, because it was that one link. So one link got screwed up. What about the other links? They're still good. They didn't have a problem. Spanning tree would have actually said, oh, I got an isolated path here. Look, I'll bring up this secondary path. It would actually fix it. What happens with VPC? Well, if VLAN 10 is a new VLAN, this is where it gets fun. Because it's not on the other switch. So what we normally say is the common VLANs stay active, right? Well, in this case, I don't have any common VLANs. So there's a mode in VPC that you can say the device that's role primary will actually take in ownership. So if I have a bad config on one port, it doesn't affect the other side if he's primary. So if you always remember to do your secondary first, you can actually fix it. Now, what happens with a reload or a peer switch or that peer link failover? Your role switch. So now you're guaranteeing that somebody who actually looked before they logged into the switch and didn't assume that he was primary or secondary. So I've had a lot of problems with that over the years with just a simple command. The F3s have fixed a lot of my problems because of max scale issues. F2Es, I had a lot of accounts that actually hit 16,000 MAC addresses. It seems like a big number, doesn't it? It blows away in some accounts pretty quick. So we had to always do tricks to basically shift L3 off of those cards if at all possible. Also, when I look at VPC's maximums, this is a great reference slide because we're not going to go through all of them. But just realize, if I have a lot of servers, I only have 576 VPCs. So if I have a whole bunch of servers connected to a whole bunch of FEXs going into a pair of 7Ks, or a pair of 9Ks, or a pair of 5600s, I can easily blow up this number pretty quick. So again, horizontal scale is a good idea in a lot of cases. So we talked about the consistency check problem. Type 1 errors, type 2 errors. Be careful about that. And this is the slide. So in this case, somebody typed in the command, switch port allowed VLAN 105. What happens? Well, only VLANs 100 to 104. I have to isolate all my VLANs in this case because I'm inconsistent. So unless I change the default behavior of the switch to say the primary one takes control, by issuing this command, you have an outage. You can basically isolate a landscape inside your environment. All right? So that's what I don't like about VPC. I like them. I use them all the time. In every design we talk about today, I'm assuming VPC is there. But I like VPC when it's on my top of rack switches, not when it's my whole environment, if I can get away with it. I'm assuming every single person in this room has VPC configured at some point in their environment. It's not bad. It's just understand that problem, right? Makes sense? Bored to death? We only have another hour. Okay. So let's say, so I looked at the other design. I have these these two extra magical, floating ovals. I go back to that last design and I say, great, I can just scale this. I can create cookie cutters of this design, and here's my building blocks. I like to do fabric path. I still do virtual port channels at the top of rack switch. I still do VPCs going down to my FEXs, like the dual attached FEX if I had that requirement. And then I'll do a VPC going to the server itself, the dual attached server to both FEXs. It's a great design. My 5 largest customers and my smallest customer are all fabric path shops. And depending on the age of their data center, in a lot of cases, like their one data center is a VPC fabric, and their second data center is usually fabric path data center, because then they alternate every couple of years. They upgrade a data center. So every 3 to 5 years, they upgrade data center 1, then they upgrade data center 2. So now we're in between. So we don't have common technology in either data center. I have VPC in data center 1. I'm usually fabric path in the second one that got upgraded. So they work together. You never get rid of VPCs because, again, it's always that connection in between the two. There's a lot of things that fabric path does without you needing to know about it. It actually creates an ISIS routing protocol under the covers that you don't have any access to. It runs it. It builds up neighbor relationships. It exchanges routes. All you do is do switch port mode fabric path on the interface itself and enable the license in the feature set. In this case, when I come in, I flood try and talk to C inside of the environment. When I flip this over to fabric path, when the packet comes in, I do a route lookup for where that destination MAC address is. When you look at your MAC table, the cool thing is you'll see C if you have traffic to C, because it does a concept called conversational learning we're not going to talk about. But when it does a lookup on C, it'll say that the MAC address for C is on switch 42. So now I route the packet to switch 42. I put a header on it, destination port or destination switch 42, source switch 11. I send it to the spine, and he routes that across the fabric. And if I have multiple spine switches, guess what? ECMP routing across all the spine switches in the environment. So I have my headers, I route the packet, and then once I hit that egress switch, I break it out as if it's what? A standard Ethernet frame. I can't switch a server, right? The server needs to function with ARP and everything else like before. I'm just saying, I'm going to hide that from you. I'll make Ethernet and TCP look identical, but the way I'm forwarding packets across my fabric, I'm just going to do it on my own. So we do use ISIS. If you actually spend the time to go through it, you can actually see the ISIS routing protocol for it, but it's kind of hard unless you really, if you know ISIS, you can find it and you can see it, but otherwise it's just there. We do ECMP. So in this case, you'll see, here's my switch IDs. So I'll know switch 1 is on link 1, switch 2 is on link 2, all the way down. And if I'm trying to get to any of the other leaf switches, I'll see, hey, I got 4 paths. This is just like ECMP routing. And then when I do that MAC lookup, there's 2 things you do. First, you look to say, where's that MAC address? That MAC address is on switch 42. So then I do a routing lookup. How do I get to switch 42? I route switch 42 through link 1, link 2, link 3, or link 4. Those are my 4 equal cost routes. Which one do I choose? I can't tell. There's actually a show command where if you put in the source destination IP, all the port information, it'll actually tell you which path it's going to use for the flow. I send the packet on. I can load balance them, and they're off on their way. How many people do fabric path here? Okay. There was a tectorial on Monday, and there was about 100 people in the room. The guy's like 80% are fabric path shops. So a lot of people still use fabric path right now. The thing that I like to think about when I do fabric path, though, is where do I do L3? Where's your L3 control point? Now, a couple years ago, with the F2 cards, we started blowing out the F2 cards from a MAC address table perspective. Because if I go back to this design, these 4 switches, switch 1 to switch 4, would be my spine. If I did L3, kind of cool, I could do L3 across those 4, right? I could have the same default gateway or the same virtual gateway be across all 4 of these switches from a horizontal scale perspective, and I could actually do my L3 there. However, if I'm doing L3 at the spine, there are some limitations that I want to keep in mind. The first is the spine will have to learn all MAC addresses. In a normal fabric path deployment, the spine, unless there's L3 on the spine doesn't know a single MAC address. The spine only knows switch IDs, and because he's a giant router. All he's routing for is where are my switch IDs and how do I route between my switch IDs. If I know all my MAC addresses, I got to worry about, well, what is the MAC address table size on that switch? You could say, Jeff, I got like 500 servers, 2,500 VMs, 5,000 VMs. Okay, it doesn't matter. The thing that does matter, though, is something called an overload bit. With ISIS, that's our routing protocol we're using. So I'm creating routing. I'm routing between all my switch IDs. I'm routing my MAC addresses. I route MAC addresses, and I exchange that information through ISIS. Okay, I reload a spine switch. Well, if I'm doing L3 at the spine, we actually create a VPC at the spine. Even though none of the ports are in that VPC, we use VPC, so guess what happens? They can both answer for those virtual MAC addresses, right? They act like one logical switch from an L3 standpoint. Well, there's also a virtual switch ID for spanning tree. So it's not switch 1 or switch 2, it's switch 102, right? It's a virtual switch. When that spine goes down, he's going to come back up. When he starts coming up, he starts doing this ISIS negotiation, and he starts trying to figure out where's my routing tables, where are my MAC addresses, who do I talk to? He's building a routing table. Guess what? ISIS takes a little while to get started. Once it's up, it's great. So we started doing something called an overload bit. And an overload bit says, I'm too tired. Enough. I've had enough of an hour and 45 minutes of you, right? I'm done. Until you're ready. And then, after so many minutes, once your neighbor adjacencies are all built, you withdraw the overload bit and you become an active member of that routing table again. I can't do the overload bit currently if I do VPC in the spine. I can't basically suppress sending out my virtual switch ID. So when that spine comes up, you'll see a blip in your traffic flow and your fabric because of it. All right? We use timers and other things to help tweak that, but you will see a blip when that spine comes back online. Make sense? Okay. So I don't like blips. So what I like to do is I like to actually move my L3. If I take my L3 and I remove it from the spine, I have a lot of places I can put it. So one of the cases, I'll actually put it in the access tier. I'll show you in a couple slides what this looks like in a minute. I deploy this in the access tier. I can scale horizontally. Overload works on startup for faster failover. And all my L3 is done at a common configuration point. So I like this design. If at all possible, I actually do L3 at what I call a border leaf, which is just another leaf switch. Any fabric. You talk to the guys, like the ACI deployments, everything else. Where are we doing our L3, guys? On leafs now. Right? We're not doing it on that. It's no longer north-south traffic. It's east-west inside the data center. So why are we still doing what we did 15 years ago? So I'm starting to move that back down to the leaf. Overload bit works. I get MAC scale a little bit more because I'm not worried about MAC address table limitations per box. It's horizontally scalable. Or we started doing this concept of distributed gateway where each leaf node could actually be an L3 point for all your VLANs. So now, let's say I have 10 access tier switches. You guys are a pair, you're a pair, you're a pair. Guess what? You're handling for VLANs 1 through 10. You're handling VLANs 1 through 10. You're handling VLANs 1 through 10. We basically stop L3 at that first demarc into the system. So now I have an ARP flood. Guess what my region is? My availability region. My availability zone. I think that was my word. Availability zone inside of a region. The region would be this fabric path domain. My availability zone would be that L3 control point. So now I get an ARP flood. What does that do? All the ARPs are terminated at that one box. It doesn't cascade through the rest of the environment. Really slick. So you can see all these badness in the network is actually contained when I push distributed gateway out at the leaf. So Lucas Kratiger has sessions on DFA that talks about optimized networking, where they push that L3 down to the access tier, which is what that concept is. So a little bit more. In this case, I have my switch. He comes up. Both of these guys are active. I'm using fabric path in between it. I create still a VPC. It's a VPC plus now. And the only difference is I'm running fabric path across my VPC ports. They're not standard switch ports anymore. So I just type in my VPC peer links. I do switch port mode fabric path. My VLANs are all mode fabric path. They're connected together. Now, when he tries to hit his default gateway, he can go to switch 1 or switch 2. It doesn't matter. Nothing's actually running fabric path. Again, there's an emulated switch ID. This is switch 121, switch 122. The emulated one might be 123. So just realize that overload is not going to work in this case. I can't use it, and there'll be a blip if one of those switches come back online. This is what I like to do, if at all possible. And I'm not doing optimized networking. I have my servers connected to FEXs, single attached or dual attached, where servers VPC'd into 2 access tier switches. I use fabric path in between these 2 nodes. You see this little line here? That's a port channel. Why is that a port channel? If I have a loop, there's something in fabric path. Fabric path, everything's 40. There's no spanning tree. But guess what? We still build a tree. We build a tree for what's called BUM traffic. Broadcast, unknown unicast, and multicast. That's BUM. You always got to figure out how to deal with the BUM. If I created a 10 gig loop, guess what? That would actually be sent directly up to the multicast root bridge that's handling that broadcast, unknown unicast, and multicast traffic. If that's a 10 gig loop, I have 10 gig of load. So what I always like to do is have that ports in between my leaf and my spine at a higher bandwidth level than my traffic going to the servers. So I can never actually saturate it, so I always do port channels there. Even if it's 40 gig, guess what? I always do 2 ports per switch, and I bundle them together in an Ether channel. You could argue that I can do everything through ECMP with just having routing take care of it, but because of multicast, unknown unicast, multicast, potentials for loops, I always do Ether channels. I can also scale this horizontally. In this case, I actually had, so this is a, I don't know, they're Fortune 50, I guess. A very large German company. We put all their L3 on 2 7Ks that are actually Ether channel connected into 2 top-of-rack switches. These are M2 cards up here. Here's our 5600s. I take an OTV VDC, and I actually tie my OTV directly to my border leaf. Firewalls, load balancers, I connect them all to leaf nodes. Nothing goes to the spine except leaf nodes. L3 is all done outside of the fabric. Anything that occurs out here from a looping perspective, anything doesn't actually affect the overall fabric operation. And that to me is the key. When we define this, we always want to set your switch IDs. We'll dynamically negotiate them for you. Set them. You decide what they should be because you want to troubleshoot them in the future. Now, I don't really troubleshoot fabric path because the thing's been stable at every one of my accounts so far. I shouldn't say that, I guess, on stage because then they'll call me tonight at their afternoon, my morning, or my evening. When I do this, if I'm creating a border leaf, I always actually make them my multicast root and secondary root. Because our multicast trees by default, we have 2, unless you actually ask us to increase them via the CLI. So if I only have 2, I'll make one of these the root, one the secondary root, which means Switch 1 is route for half the traffic. Switch 2 is route for the other half of the traffic. And we actually split the multicast range up between them. When I handle this, it gives me actually the best distribution of traffic from a design perspective. This is optimized networking. So DFA actually has 4 parts: centralized management, workload automation, cable management, and optimized networking. You can break up functions. You don't have to do all the parts of DFA. You can just say, I want to do optimized networking, for example. In this, or virtual fabrics is the last one. In this, I can say, okay, here are all my links. So I have my 2 leaf top rack switches connected. I have my server ether channel or VPC connected to both of them. And then these 2 will be the routers for VLAN 1 through 100. These 2 will be the default router for VLAN 1 through 100. So slick. Like, it's kind of cool, right? When a packet comes in, I'm making an L3 decision basically on every single packet, but I can have A and C in the same VLAN, even though they're on different sides of the data center. I think it's pretty cool. When you look at some of the stuff we're doing with VXLAN gateways, same idea. Every top-of-rack switch masquerades as every other top-of-rack switch from a routing perspective. Nobody, like, I think it's pretty cool. So in this case, it gives me full scale, and now I'm doing is routing, creating a horizontal, basically routing table for whatever needs to go across the fabric. So we're not going to go into a ton of detail on this, but just realize that that is an option for you. Now, if you're following the presentation, you'll notice that the presentation that's uploaded, I've hid like 20 slides so far, or 10 slides. So just like if you're following, like why is he skipping these slides? Because I hid them. So you'll have them. I didn't want not to put them in the deck because then you wouldn't get a copy of them. So there's some reference slides and stuff like that for you. All right, we good so far? Okay, last section. You're almost done with me. You should be happy. Overlays. So what's an overlay? It's basically just saying, you know what, I got a logical network, and on top of this logical network, I'm going to create a whole bunch of mini networks, and I'm going to subdivide it from a reachability perspective. Okay, and they're going to be programmable based on what I need to do, and they're just kind of like over the top. When you look at it, there's a couple things to keep in mind. And this could be an ESX server. This could be like ESX 5. This could be 5.5, 6. This could be a KVM. This could be a Microsoft node. If they're doing an overlay, all we're doing is we're taking the traffic from the VM. The VM has no idea about the overlay. He's going to send a standard packet, red VLAN, blue VLAN, or green VLAN, into the virtual switch. Based on that VLAN that you got sent to that virtual switch arm, that VLAN on the host is correlated to a VNI most likely. You can also do GRE encap or NVGRE for Microsoft. So now I'm going to encapsulate the packet and I'm going to send it to the destination. So if VM1 wanted to talk to VM4, I would just put that into a header. I'm routing it now across my IP network between, host 1 running 111 and host 2 running 222. The source IP address is this. The destination IP address is that. And then there's an identifier in the packet to say, well, what VLAN was it? And that VLAN correlates to something like a GRE identifier, NVGRE header, or a VXLAN virtual network identifier. The hypervisor-based, I forgot GRE because KVM will run just GRE or VXLAN. VMware runs VXLAN, and Microsoft runs NVGRE. In addition to the overlays, though, there's other types of network-based overlays. I can look at OTV, VPLS, eVPLS, Fabric Path. They're all actually network-based overlays. Now, you might not, why is hypervisor, why are VXLAN and NVGRE actually network overlays? Because the network can actually just take VLAN traffic, encapsulate it inside of a header, and actually that becomes my routing table or my routing fabric. So it's not only is it a hypervisor overlay, it's also a network overlay. And I have a customer design right now where we're actually using VXLAN as a network overlay, but the servers are still using VLANs. We're just encapsulating it when it hits the top of rack switch, and we're actually creating our own VXLAN fabric for routing in between the sites, or in between the data center. I'm sure everybody wants to study this incredibly much. The things that I want to take out of this is the VXLAN identifier, think of it as almost two 802.1q headers. So instead of being 12 bits, they're 24 bits. 2 to the 24th is 16 million. Do not assume that you can have 16 million VLANs or 16 million VXLAN networks on a switch. The switches are still bound, right, to a construct. The other thing to keep in mind is I have to break VXLAN and VLANs are actually interconnected a lot of times. Because I might have a VXLAN on for a VM, but if he needs to get the storage on that same network, guess what I need to do? I need to actually take away that VXLAN header and correlate it back to a VLAN. Or I need to strip it, VXLAN header, and give it back to an SVI on the switch. So all these things, that you start seeing a relationship at times. There's some VXLANs that are going to be totally isolated that we'll never see it. There's other ones where we'll actually get involved and you'll be correlated back down to the VLAN structure on that switch itself. So the VMs do not see the VXLAN identifier, which is kind of slick. The default standard, and this is what's interesting, is it's IP multicast. When you read the RFC, it'll talk about the opportunity to have extended control planes in the future. But the standard one right now is multicast, and then there's some competing standards for OVSDB and EVPN are the two competing standards. We're trying to be better, not competing, but try to be better control planes for VXLAN traffic in general. VXLAN or VLANs, 4K, 16 million. I have customers that don't really need more than 4,000 VLANs. The issue is that they duplicate VLANs in different parts of their data center, so they're actually looking at VXLAN as a way to create isolation between overlapping VLAN identifiers. Kind of slick. So I don't necessarily need more than 4,000, but I might need 4,000 just overlapping IDs that I had in the environment. So somewhere between these two would be, I guess, the answer. A lot of the things that we use, so I do have certain designs. We have something called virtual containers, VACs. And in the VACs, when you set it up, you'll actually have like an app tier, a database tier, and a VM tier, and they're never exposed. They're only isolated for communication between these little tiers. And if I need more performance, I actually take this container, not Docker container, a container of VMs, and I actually clone that repeatedly to meet my performance requirements. But when I clone that, guess what happens? Well, I'll actually have these little mini VLANs. When I clone them, I could potentially, depending on how I do it, have duplicate IPs and duplicate MAC addresses. So the way to create that isolation is to have different VXLAN identifiers for each one of those, so they can't see each other and they can't cause contention. And then I'll use a gateway to basically NAT the traffic in and out of that virtual app. There's two ways that we can have gateway functions. There's L2 and L3. A lot of people out there are doing L2 gateways right now, which basically say VXLAN traffic comes in, I take it, and I just say there's a VXLAN identifier 1,000 or 10,102, and I just break that out to VLAN 102 on the other side. There's no L3. There's no SVI. I'm basically just taking traffic in from a VXLAN and dumping it out onto base VLAN. Okay? That would be an L2 gateway. The other function is where you actually get that VNI and you make a routing decision on the VNI itself. So VNI 1 million talks to VNI 2 million, and I route that traffic in between the two, or I provide a router that's basically that acted as an L3 gateway for that subsystem. Totally different. When you look at VXLAN gateways in the industry, you got to look to see if they're an L2 or an L3 gateway. You might think it's easy to find stuff on the internet, but I have trouble sometimes because it's in a lot of different places. So I made this myself. I'm very proud of my slide. But it gives you an idea of what versions of code you have for which products. So for example, NXOS 1000, that's the functionality for it. That's its VXLAN code. 3100, bridging only, so L2 gateway in 602. The 5600 is 7.1. The A, we pulled 7.11, so I thought it'd be smart to just say you can only get it in A, because the other one's gone. But that's bridging and routing. The 9K, ASR 9K is bridging and routing. The 9300 today is L2 only, and the L3 code is in something called Bronte, and that's in EFT right now. So if you need that code for 9300, contact me, and I'll get you put onto the beta list. Okay? How does this look? So in this case, I'm using the multicast control plane. So my VMs would actually join multicast group 239.111. And now, whenever they want to communicate, they'll actually send stuff to that multicast group. And in this case, I have another multicast group for the database VNI, or the database VXLAN network identifier, VNID or VNI, you'll see it referred to, VNID. I'm going to then create, in this case, an ARP where I want to find how do I talk to VM2. So I'm going to say, I want to go to this guy's IP address. I'm going to send it to that multicast group. It'll hit the core, broadcast, unknown, unicast, multicast packet. I will then replicate that, and I'll send it out to any other VTEP that's joined that multicast group. Make sense? So now, I'm going to forward it to both those guys. Switch 3 just goes, or VM3 goes, I don't know who you are. I don't have that VM. He throws it away. VTEP 2 will de-encaps the packet, send it back to the VM2. But the cool thing here is, as soon as it got that packet, it knew that VM1 was where? On VTEP 1. So he actually puts that into his table just by getting that ARP request. Now VM2 says, hey, that's me. He creates a response. The response, though, goes directly to VM2 because he already knows where he is, right? He already knows that VM1 is off of VTEP 1. He then routes the packet across the infrastructure. It routes back to VTEP 1. He de-encapsulates it, and he sends it directly back to that VM. And now they have unicast traffic going in between them. It was only that initial ARP packet that was multicast. Everything else was what? Unicast. Kind of slick, right? I still have to take care of how do I handle that multicast traffic. So I get a lot of requests to say, okay, I know I'm said VXLAN, it's going to be cool, but I still have a lot of bare metal servers. And that bare metal server needs to participate in that same network. Not a problem. In this case, I created a couple things. I had to turn on features, and this is the NXOS commands. The router commands are slightly different. Like an ASR doesn't do features, right? So small differences. I do feature VN segment VLAN and an NV network virtualization overlay. I create my VLAN 102, and underneath it I associate it to the VXLAN identifier. In this, then, that's 10,102. I try to keep 102 in there just so I could remember. And then I do interface, network virtual interface 1. I source it based on the loopback address. That's the address that I'm using for my VTEP, because now I'm a VTEP just like everybody else. So now my VTEP address is based on my loopback address. I create a VNI member of 1002 relative to this virtual tunnel interface, and I associate what my multicast address is for it. And then, for that bare metal server, or a server that was not using VXLAN, what do? I just say VLAN 102, and I connect the server to that port, or the storage to that port, and guess what? It just works. So now, I become that L2 gateway between that VTEP on that hypervisor and the other physical server inside the environment. So a couple new commands like NVEs. Now I'm most likely going to have one NVE. I could have 1,000 VNIs, but they're all going to be under that one NVE interface. Okay? The L3 gateway, the thing that changed here is, well, my VN segment VLAN, my feature NV overlay, they stay the same. Feature interface VLAN, because I can't do an L3 interface on a switch without that on a NXOS, right? Feature PIM. This is an L3 box. So now, same thing, VLAN 102, VN segment 10,102, interface loopback 1, same thing. This is my address that I'm using for my VTEP. I have to put it into a routing protocol. I used OSPF because I was doing this on a 9K, and it supports OSPF. So I did OSPF today. I then do IPPIM sparse mode, enable my multicast. I do a no-shot on the interface, same config as the last system. Exactly. What's different? First thing, I'm creating PIM, so I'm enabling feature PIM. I'm defining where my routing point, my route map, because all my multicast, my VXLAN is the 239.1.1 network. So I'm saying 239.110/24. You can be an RP, and this would be on that L3 gateway upstream. I'm defining what my RP, my Anycast address is, in this case 10.10.10.50. I define what addresses I want part of that. So that rest of that multicast config is guess where? Slide 54. And I actually paid attention, made sure it was there. I then define my interface 102 or 2/1, and this is how I'm routing through my core to get back to my aggregation tier or my spine where my RPs are. Okay? So I'll just have that. Besides that, only thing different between the last two slides is, one, I enable my, my PIM routing. I created an L3 uplink to my core, and right here, what did I have? I just gave an IP address to VLAN 102. Besides that, it's identical to the last example. It's not that hard. The one thing you want to consider with VXLAN, though, is this. If somebody, VXLAN has no control plane. Right? It's flood and learn. So if somebody made a mistake and decided to take switch 2 and connect it to switch 4 via cable, like who's never seen two ports on a hub connected together in their life? Like stuff happens, right? If they did that, you're creating this spanning tree loop because VXLAN won't try to block it. It's a routed fabric with a tunnel. The network doesn't see it. Ooh, that's a problem, right? So how do I stop two switches from being interconnected? APU guard. So I go to all my host ports. Now my uplinks, I go to all the host ports. I do spanning tree port fast, type edge trunk, and I turn on BPDU guard on those, and I'm off and running. So keep that in mind. There's also cable management designs you can do with like DCNM to make sure that leafs aren't connected to leafs and stuff like that, but that's the most simplistic way. OTV, though, what I like about OTV is in this case, I can have a loop, right? In this case, I can't because there's a control protocol that's blocking all that. A control protocol that's stopping spanning tree, a control protocol that's suppressing ARPs, things like that. So OTV actually fixes a lot of things for me. So it handles all the broadcast duplication, loop handling, egress route optimization. It's all built into it. So now, in a lot of the designs, like I mentioned before, I might have two data centers, one fabric path based, one VPC based. I'll just use OTV to take my critical VLANs and tie them in between the two. Okay. But you have to decide how you want your routing to occur. By default, what a lot of people will do, if you have firewalls or asymmetrical points and you want to create symmetry in your network, they might have the HSRP active on one switch in the data center 1 and actually have the other data force all the traffic to be tromboned to the primary site. So in this case, if the green server wants to talk to the red VM at this data center, they would actually have to send it back to data center 1 and go back again. That would be the default behavior. What we've done, though, what I like to do, if I can get away with it, is I'm like, I don't want tromboning. So to get away from it, I want to force basically HSRP packets to be blocked in between these sites. So I filter out my HSRP messages between the two locations. So now, if these guys want to talk, they're talking directly through their L3 switches at that site. This could be 7Ks, 5600s. The OTV right now is done on top of ASRs, CSRs, and 7Ks. That's the only place we have OTV at this point. But it allows me to basically do that filtering. So like this is built into the control plane, and I can do this. With VXLAN, I have some people that are trying to do VXLAN between data centers, and I'm like, how are you blocking gateways? Because I can't have multiple gateways in default VXLAN. Like we're doing tricks to basically do any top of rack switch, which we didn't talk about, but any top of rack switch can be that gateway and masquerade for every one of them. But that's not the standard implementation. So in this case, I'm actually handling it. The ARPs are done locally, and I just basically allow local routing between those two subnets. Even though that VLAN 10 and 20 are active in data center 1, they're also active in data center 2. When we block HSRP messages, though, the one thing we don't block is gratuitous ARPs. So a gratuitous ARP would still go through, so you'll see an error message every time there's a gratuitous ARP, unless you do this message, okay? And then with that, with localization, you just want to keep track of your filtering, your egress routing, and if I can get to this slide, so I want to go to, not just how do I handle my traffic in between, I also want to keep in mind my inner traffic or inner data center and how do I get people to the right data center. If you're doing a dual data center design, please let me know. We'll go into Lisp and what we're doing with that because it allows us to segment out how do I tell you where that VM is active at this point in time. Okay, so Lisp actually fixes where that VM is active in that instance. With that, thank you for your time. I'll be around for some questions. Here's some great books. They'll tell you to fill out the survey to get a new t-shirt. Parties Thursday night, table topics. I'm actually going to be doing Meet the Engineers tomorrow, and I have table topics right after this for the data center if you guys want to sit and talk in more detail. So thanks for your time.